Hello, precalculus class. Today's lesson is an introduction to conics. It's part of analytic geometry section. And conic sections are cross sections of right circular cones and a plane. So just notice that we have here 4 different right circular cones. So this is your right circular cone here, and we actually have a double cone. And the double cone comes in handy when we look at this conic over here. But if we take the plane, which is shown in green, and intersect it perpendicular to the axis of the double cone, you will see that the cross section is a circle. If we tilt that plane so it intersects one of the cones at an angle, you get a shape that's an elongated circle called an ellipse. If we take that plane and we intersect the cone so that it goes off the face of the cone, we actually have this curve shape, which you've done a lot of studying in an Algebra 2 class, called a parabola. And then the last conic that we're going to study in this unit is called the hyperbola. And this is where you intersect the double conic, or the double cone, and you intersect it twice. And you have a curve down here, and then a symmetric curve up here. The shape of the curve of the hyperbola is different than the shape of the curve of the parabola. One other important thing to note is that the double cone is created if you take two lines in space, and you intersect them, and then you rotate these lines. You actually create the double cone. All right, there's another kind of conics called degenerate conics, and we're really not going to study these in this section, although you've studied most of these before. These are created by the intersection of the plane and the cone, but they do not create one of the curves that we talked about earlier. If we take that plane, I'll draw it in green, and intersect the double cone right here, so it touches right there, we get a point. If we take the plane and turn it so we're intersecting this double cone right here, the intersection, or the points in common, the cross section, is just a single line. And if we take that plane and we intersect the double cone parallel to the axis so that it cuts right through here, right through the center, you actually see that the only points of intersection are going to be the edges of the double cone, which is a pair of intersecting lines. Those 3 conics are called degenerate, and we're not going to be studying those. On this slide, the first thing you see is the general equation for a conic section. And you can see it's a lot longer than equations we've seen before. So there's 2 variables, x and y. You can have the x squared or the y squared, or single x or single y. This is kind of like, your general form or standard form of a line looks like this. And then you have your quadratic equation, standard form of a quadratic. So the conic sections get longer because we're looking at some different shapes. And we can have non-functions, so we can have a y squared term. So the 4 conics we're going to study are a circle, an ellipse, a parabola, and hyperbola. And all of them can be written in this form, but certain things are going to be true, as well as they can be written in what we call the standard, or I also call it the graphing form. When it's in this graphing form, then we can draw a sketch of that conic very quickly, knowing the different parameters about it. Now, you don't need to write all these down right now. We are going to spend one lesson each day on each of the 4. The lesson we're going to spend time on today is taking this general equation and completing the square on it so that we can turn it into this form or this form or this form or this form. So we're just going to practice that skill called completing a square. And note, we're going to be completing the square like we did with quadratics, which just has one variable. But we're going to have to kind of open that up and do completing the square twice, one for the x variable and one for the y variable when we're working with conic sections. So here we're going to do a review lesson in completing the square. So if you are given a quadratic equation in the general form that looks like this, kind of all multiplied out, and you want to turn it into a form, what we call the standard or graphing form, like this, you need to do something called completing the square. So what we have down here is using variables, no numbers, kind of going through the proof of that. And the big key is you want to group these two terms, the x squared and the x term, factor out the coefficient of the x squared term, and then find the number here that makes a perfect square trinomial. So it turns out what it's going to be is b over the a, which is the coefficient of the x term, multiply or divide it by 2, and then square it. And that is the term that you need to complete the square. Now note, what happens is you have to add that to the other side as well, but this has to be multiplied by a, and you end up, it looks like this on the other side. What we're going to do is jump right down to the example, because I think in the example you won't get lost in the variables and it'll make them a lot more sense. Plus on the next slide there's a bunch more examples as well, especially one that has a not equal to 1. Right here, this example is a is 1, which makes it a whole lot easier. All right, so let's move this up and let's do the example. So the first thing we need to do is group the x squared and the linear term, the quadratic and linear term. And then we take the linear term coefficient, -6. We divide it by 2 and we square it. So -3 squared is 9. So that is the number that gives you a perfect square trinomial that can be factored into a binomial squared. And if I add it to this side, I have to add it to this side. So, and then to finish the problem, x squared minus 6x plus 9 can be factored into x minus 3 squared, and of course -4 plus 9 is 5. Let's just test that. If you do x minus 3 times x minus 3, you end up with x squared minus 3x minus 3x plus 9, which is x squared minus 6x plus 9. So note, the only number that makes this a perfect square trinomial is 9 if the linear term is -6. Now, what good is that? Well, it can do a couple things. One, it can help you solve for the intercepts of that quadratic, or the value of x in this equation. So I can do that now by square rooting both sides, and you end up with x minus 3 equals plus or minus the square root of 5. And of course, then you add 3 to both sides, and you end up with 3 plus root 5, or x equals 3 minus root 5. And those are your x-intercepts or roots. The other thing is, let's say this wasn't equal to 0, but it was equal to y. We had y equals x squared minus 6x plus 4. And when you go through completing the square, you end up with y equals x minus 3 squared. And of course, you know, this whole thing equaled y, so minus 5. And the beauty of that is it's now in this form here, this form up here. And we can talk a lot about how it would graph. Let's see. The vertex of this parabola is going to be at 3, -5. Remember, it's moving to the right 3 and down 5. So vertex is about here. And then also my a term here is a positive 1, so we know it opens up and it's not been stretched in any way. So it's like this. And just so you can see, these 2 points here, actually I didn't draw this well because this is still a positive number, but are your intercepts. So it's probably more like this and like this. And there's your intercepts. There you go. On the next slide, we'll have some more examples. All right, let's do a few more examples to get the hang of it. Why don't you go ahead and pause it now and do the first example, because it's a lot like the one on the other page, and then we will do examples 2 and 3 together. Okay, so you can see the first thing I did was move the 21 over to the other side by addition. Then I grouped my quadratic term and my linear term, and then I took the coefficient of the linear term over here, divided it by 2, squared it. And you get 2 squared is 4. So that's what completes the square. Now I didn't have to worry about the a term because the coefficient of the x squared is 1. So a is 1. So you just kind of ignore it. So when you do that, then now you can factor this. This is a perfect square trinomial, and I can factor it into x plus 2 squared, and then 21 plus 4 is 25. Really, by doing this, we have two options now. The first one is when it equals 0, you get this, so I can solve for x. So I can square root both sides and get x plus 2 equals plus or minus the square root of 25. That means x plus 2 equals plus or minus 5. And when you subtract 2, you have negative 2 plus 5, which x is 3, or negative 2 minus 5, x is negative 7. And both of those are solutions to this quadratic equation. If this didn't equal 0, but instead it equaled y, we can see that this graph of this quadratic looks like this now. And we know when you have a graph of a quadratic in the standard form, we can quickly find the vertex at negative 2, negative 25, looking at our transformations, left 2, down 25. We also know that my a term is 1, so it's pretty much a standard parabola, and it's also opening up. So if I graph that, it's 2 over and way down, and it's coming up. And then we also now know that we have an intercept at 3 and an intercept at negative 7. So it's actually a pretty steep parabola. Okay, next example. So this one, we do have an a term of 2. So the first thing I'm going to do is I'm going to factor out the 2 of the first two terms. Just check your work. 2 times negative 4 is negative 8. And I give myself my space for my completing the square value. I'm not going to factor the 2 from the 5. I'm just going to move the 5 to the other side. And if I add something here, I need to add something here. So now I can focus in, and this has already removed the a value. So I just take the negative 4, divide it by 2, and square it. And you get negative 2 squared, which once again is 4. So I'm adding 4. Well, I didn't really add 4 to this side of the equation. I added 4 times 2, or 8. And that's why you really got to be careful when the first term is not 1. So now we can finish the work. 2 and our factored binomial squared is x minus 2 quantity squared. And this side is 13. So we have x minus 2 squared equals 13 halves. Excellent. Now, if I wanted to solve for x, I'd square root both sides and get x minus 2 equals plus or minus the square root of 13 halves, and you end up with x equals 2 plus or minus the square root of 26 over 2, or depending on what you're doing with this, you have y equals x minus 2 squared minus 13 halves, and you can find the vertex and graph it quickly. The last example, we'll do this one. Note that all of a sudden, I have included 2 variables. And I did this because this is why we're going through our review of completing the square. We have an x squared and a y squared term, so I'm going to have to complete the square twice. So first thing I'm going to do is group my x squared with my x. And note, this one first term is 1, so it's an easier problem. Then I'm going to group my y squared with my linear y term. And then I am going to move the 1 to the other side. So we have to complete the square here and add both to keep the equation in balance to the other side. So negative 8 divided by 2 is negative 4. Negative 4 squared is 16. And 2 divided by 2 squared is 1 squared, or 1. And we end up, when we now factor each of these, the x separate from the y, you end up with x minus 4 squared plus y plus 1 squared equals 16. Bingo. We have completed the square on this conic section. And we're going to learn about these more tomorrow, but hopefully you do recognize that equation of a circle with the center at 4, -1, and a radius equals to 4. If you don't, that's okay. Your homework is just going to have completing the square on single variable or quadratics.